This video is the third in a series about the A-level chemistry topic of alkenes. We'll quickly recap what we know about polymers from GCSE chemistry and then look at how what we've learned elsewhere in the A-level course impacts on those things here. In GCSE chemistry, you learned that polymers were very long chains made from repeating units called monomers. The monomers are bonded together in the chain by strong covalent bonds, but then there are weak intermolecular forces between the chains. Now, obviously at A-level, we can name these as van der Waals forces. And we know that larger molecules have stronger van der Waals forces. And so, since polymers are very large molecules, they have very strong van der Waals forces. These are much stronger than small covalent molecules like the monomers that they're made from. And this helps us to explain why the vast majority of polymers are solids at room temperature. If you took GCSE chemistry as opposed to GCSE combined science, then you also learnt about addition polymers as contrasted with condensation polymers. Addition polymers are made from molecules with double bonds, so that includes alkenes and also substituted alkenes, so halogenoalkenes and things like that. If we look at a monomer, then we can see the double bond which will break and polymerize, leading to this polymer. We use the repeated unit nomenclature as a shorthand for a much larger molecule, in which this repeating unit is just repeated over and over. It's also important that we name polymers according to their monomers. So this polymer is polychloropropene. But remember, despite the name and despite the fact that it has an -ene suffix, this polymer doesn't contain any double bonds anymore. So it's actually a halogenoalkane. So before we go any further, let's just check that you're comfortable taking this displayed formula of this monomer and drawing the displayed formula of the repeating unit of the polymer that it will polymerize to form. Hopefully you've drawn something that looks a little bit like this. So crucial things to note are that we've got the brackets around the repeating unit. We don't have a double bond in the centre anymore, it's now a single bond. And the N to show us that there are many repeating units is on the right-hand side, not the left-hand side anymore. Many exam questions will ask you to name a polymer, and they may make this more complicated by giving you quite a complicated organic molecule. But let's check here that we're happy with how we could go about doing this using something much simpler. So the first thing that you need to do is to identify the constituent repeating unit by breaking the chain up into identical repeating pieces. Once we've identified this repeating unit, then we can move on to thinking about the monomer that it was made from. So here I've got my repeating unit, and if I was going to draw this out fully, of course I put brackets and put the N to show that there are thousands and thousands of this repeating unit. Now if I was going to draw the monomer that it was made from, it would look quite similar, but it wouldn't have those brackets anymore, and of course it would have a double bond in the middle. We put halogens in alphabetical order, so this is going to be 1-bromo 2-chloroethene, and therefore the polymer is going to be poly 1-bromo 2-chloroethene. In this question, we're not being asked to name the polymer, just identify the monomer, and the repeating unit is already given rather than that fully extended form of the polymer. But I still need to do a little bit of thinking to figure out what the monomer might be. So your first instinct should be to count up carbons, but remember, we're thinking about the longest carbon chain, not all the carbons in total. So although I have 5 carbons in total here, they're not forming one continuous chain. If I number them up here, I can see I've got 1, 2, 3, 4 in a chain with that second carbon having a methyl group coming off it. It's always worth double checking if you count from a different place, do you get a different number? Because that could be relevant if you've got, say, an ethyl group or a propyl group that might catch you out. But here it's a methyl group, so even if I count from the top instead of the bottom, I still have a carbon chain that's 4 long, and then the second carbon has that methyl group on it. And of course in the monomer, I'm going to have that double bond between the second and third carbon. So if I was going to name this monomer, I've got a chain that's 4 long, so that's but2-ene, and then I've also got this methyl group coming off it, so it's methyl but2-ene. You're already aware from GCSE chemistry that polymers tend to be solids at room temperature, and we've discussed the fact that that's because the weak intermolecular forces, the van der Waals forces that hold those chains together, are very strong by virtue of the fact that the polymer chains are very long. But another thing that you might not have thought about is the fact that generally these polymers are chemically inert and non-biodegradable. And this is because we haven't got any double bonds anymore. These are saturated molecules, so we don't have those regions of high electron density to attract electrophiles, and also very often these side groups are non-polar and therefore they're also not really interacting with anything else. So a typical exam question might ask you to justify why the melting point of polypropene is higher than the melting point of the monomer that it's formed from. So here we'd be saying it's a larger molecule with more electrons. So we need to be making a comparative statement because it's a comparative question. And therefore, because it has more electrons, it has stronger van der Waals forces between the molecules. Another typical exam question might ask us about a specific polymer and ask us about the different properties it might have. So pause the video quickly and see if you can answer this one. Well, the first option about turning bromine water colourless is in there to catch out those of us who see propene in the name and think, oh, that means it's an alkene. But as we discussed, there isn't a double bond in the polymer anymore. All those double bonds have opened up, so it's not going to decolorise bromine water. It's formed by the condensation polymerisation of propene monomers. Again, it sounds like it could be likely because we do have propene monomers, but not a condensation polymerisation reaction. This is an addition polymer. And then if we look at D, the relative formula mass of propene is going to be 42. Whereas the polymer is going to be 42 multiplied by however many monomers are in it, so it's not that. So our correct answer is going to be C. The specification says that you should appreciate that the knowledge and understanding of how polymers are produced and their properties has developed over time. So there are two main things I would include under this umbrella. The first one is familiar if you took GCSE chemistry as opposed to GCSE combined science. Polyethylene is a really common and useful plastic, and there are two main types, low density polyethylene or LDPE and high density polyethylene or HDPE. They're both obviously made out of the same monomer, ethene, but what's different is the reaction conditions, and these lead to different properties in the polymers that are formed. Low density polyethylene is made under very high pressure and pretty high temperature too, and oxygen is included as a catalyst. When the polymer forms, it makes lots and lots of branches, and those stop the chains from packing too closely together. In contrast to that, high density polyethylene is made under relatively low pressure, maybe only 10 atmospheres as compared to about 1,000 for the LDPE, and also a slightly lower temperature, probably about 100 degrees C. It also includes a kind of catalyst called a Ziegler-Natta catalyst. Now, the impact of all of those things is that instead of getting this amorphous structure where LDPE is very, very branched, HDPE has a crystalline structure. So all of these threads are sitting very nicely together because it's comparatively unbranched. You're maybe getting one branch for every 200 carbon atoms in the chain. And so this means that the polymer chains can stack together much more closely, and therefore it's much harder and denser. The second polymer we want to think about is polychloroethene, more commonly known as PVC, because its old school name is polyvinyl chloride. And this is a really common plastic with many uses. PVC contains these chlorine atoms in the side chains. And as we know, a chlorine carbon bond is really quite polar. So you're going to have a permanent dipole set up where the carbon atom at the centre of the chain is slightly positive and the chlorine atom, which is more electronegative, is slightly negative. So you get that permanent dipole. And that means that in between individual polymer chains, we're not just going to have the van der Waals forces, we're going to have much stronger permanent dipole interactions. And so this is going to make unmodified PVC very rigid and very hard. It's also very waterproof. So it's a good choice for things like plumbing and construction. So here is our unmodified PVC, all of these polymer chains very, very closely together. And so they have these weak intermolecular forces between the chains. But then if we introduce another molecule, this plasticizer here, then that is separating out those polymer chains slightly. So here's one example of a plasticizer, and sometimes this will be included with questions that ask you to do something like count the number of hydrogens in this molecule or something. So the point of that plasticizer is that it's keeping the chains further apart and weakening the weak intermolecular forces between them. And so what that's going to do is increase the flexibility and reduce the brittleness, and this is going to make the PVC much more appropriate for things like packaging or fabrics for clothing or the insulation around electrical cabling. Basically anything where that PVC needs to be able to bend and flex without it being rigid and shattering. Thanks very much for watching, and I hope you're now feeling much more clued up about addition polymers for A-level chemistry. If you did find this video useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.